mixtape we were playing for you. So today's seminar will be given by Peter Geelan-Small, and he's going to talk about the T-test and actually regression and how the T-test is a special case of regression. So before that, I might just give a little overview of what we do at Stat Central in case this is your first time at the seminar. So Stat Central is the statistical consulting unit at UNSW, and we help anyone from around the uni with their statistical problems. So anything from design advice. So all UNSW researchers can have free design advice, free design and analysis advice to HDR students, so PhD and Masters by Research students. We do free statistical review of grants or ethics proposals, so get in touch with us for that. We also run lots of short courses and these monthly seminars, which you're always welcome to join. And then we have a couple of partnerships, or quite a few partnerships, where one of our consultants will spend a day a week in a lab or a unit or a school. And also we do contracts for sort of bigger statistical jobs. So that's what we do. To get in touch with us, you can just Google Stat Central at UNSW or email us stats.central@UNSW. This week, I also wanted to point out specifically the UNSW coders. So this is a brand new R user group that's starting at UNSW. This is their website. What's going to happen is the first and third Monday of each month, there'll be an event. So the first Monday, there'll be some workshops, and the next one is in July on how to build websites with Blogdown. And then the third Monday of each month, there'll be a drop-in session. So if you use R and you want to help other people or need some help with your own R, you can just drop in 2:30 through 3:30 on Monday at Matthews and have a look at their website for future seminars. Okay, so without further ado, I will leave the stage to Peter to tell us all about T-tests and regression.
Thank you, Gordana. I'll just share my screen. Can everyone see the title slide? Is that sharing?
Yes, we can see that.
Okay. I'll start with an acknowledgement of country, and then I'll get into T-tests. I'd like to acknowledge the Bedegal people, who are the traditional custodians of this land. I'd also like to pay my respects to the elders, both past and present, and extend that respect to any other Aboriginal and Torres Strait Islander people who are present here today. So now we'll get going. Can you see a different slide?
Yes, I can.
Okay, thank you. So why bother thinking about T-tests and regression and whether there's any link between them? The reason for doing this is that a few weeks ago I was talking to someone and they were saying, well, there's all these statistical tests, there's T-tests and ANOVA and regression and ANCOVA, and when can I use these tests and in what situation? And I thought there's really too much detail here, and it would be useful to see some of the commonalities amongst all of these things. It's fairly understandable to think like that, though, because all of these methods were developed at different times over the evolution of statistical science. Like regression was first developed in the 1820s, and then in the early 1900s, the t-distribution was developed by Gossett while he was drinking Guinness in Dublin. And then in the 1920s, 100 years ago, ANOVA came on the scene, and not long after that, ANCOVA. But in the 1970s, and that's 50 years ago, there was a lot of work done on unifying all of these methods and extending them to include other types of models, which we're not going to talk about today, but that work established the commonalities and really formalized the commonalities between all these things. And yet 50 years later, we're still looking through software menus at Ttest and ANCOVA and ANOVA and regression and thinking, well, we've got all these different methods. Let's look at some common ground. So just a couple of introductory things to set some limits to what I'm going to do. Sensible statistical modelling really starts with your research questions that you set up your study around and the statistical analysis plan that you write based on those questions. It's not so useful to ask what sort of statistical tests do I need to use, because that gives you a sort of a flowchart approach where you see this chart with lots of lines and paths linking all these different, what appear to be different things. And that obscures the unity behind a lot of these methods. It's better to ask, well, I've got my research questions and I've collected this data to answer them. How can I actually use that, those variables? Sorry, I just realized I had the video turned off. How can I use those variables that I've got to answer the research questions for the study that I have? And it's much more profitable and useful to focus on the relationships between variables. And if you do that, then you actually start to realize that there aren't quite so many different methods out there as there might seem to be. So what I'm going to do for the rest of the time is basically show some examples. The data I'm going to use comes from a randomized controlled trial that was run over 20 years ago on the effect of hormones on preventing heart disease events in older women. You can get the data at that reference I've got there if you want to play with it. And I'm going to do a range of models starting with regression. So we're going to sort of start at the end and then work back to t-tests, which might seem counterintuitive, but hopefully that'll work. One of the things I'm going to sort of focus on is model equations, which might seem a bit technical, but then probably not as complicated as they might seem at first sight. And they're a really good way to focus on what you're actually doing in a statistical analysis. And they do form the link between your research questions, your hypotheses, and the analysis that you're trying to do. There's a bit of a technical point about what actually makes a linear model linear, and we're not going to go into the technicalities of that in any detail, but just make a couple of points about it. And at the end of it all, hopefully, you might think that there really aren't quite as many different statistical techniques around the place as there might seem to be. A couple of other notes too. What I'm going to do is not an orderly analysis of using this data set. I'm just going to pull out types of models to demonstrate the points I want to make for today's topic. The types of response variable, actually there's only one response variable I'm going to use, is continuous, and it makes sense to use a model based on a normal distribution assumption. So all of the models we do are going to be based on that assumption. And another thing about modeling is that you should check all the assumptions when you do models, but I'm not going to do that because that's not really necessary for the purposes of today. So the data, there were 2,700 subjects in this study, and there were 37 variables that were measured. You can see some of the variables there, and we're going to use some of those, and they're the sorts of variables that you'd expect in a study of this type, focusing on heart disease. Age is in there as a continuous variable. BMI is body mass index for people who aren't from health. It's based on a calculation involving height and weight, and it is basically a measure of your body size and shape. There's other categorical variables in there, like exercise, yes or no, diabetes, yes or no, and glucose is the baseline glucose level for all the subjects at the beginning of the study, and that's the response variable we're going to look at. The other thing we're going to do is just look at the non-diabetic subjects. So we're going to just take a subset of those out of the data, which leaves about 2,000 in the data set, I think. So let's start with a question. Can body mass index predict baseline glucose level? You can see on the left there that we have a plot, and we've got two variables here, glucose and BMI. Glucose is continuous, as is BMI. And as I said before, these models assume a normal distribution. And what we're going to do then to answer this question is to see if a straight line model is useful. I mean, we're going to presume it is. I'm not going to do goodness of fit checks around models or try and find the best models. I'm just going to use certain types of models and show the model equation for each one so that you can see the commonalities in these different techniques. So we're going to put a straight line through that data, which sort of makes sense when you look at the cloud of points there. There seems to be a fair bit of variability, but a straight line might tell us something. As all of you have seen before, the equation for a straight line is in that form in the bottom left. We've got the response, and it's explained by an intercept, which is beta naught, and a slope parameter multiplied by the explanatory variable. So beta naught's the intercept and beta 1's the slope, and x1 is the explanatory variable. So when we fit that model and we check the assumptions, we'll do this once. The assumptions here, or two of the important ones, are that the variance is constant, and you can see that in the residual versus fitted values plot on the left. That seems to satisfy that assumption pretty well. And the normal QQ plot on the right also seems to be reasonably okay. So we've looked at the assumptions and they seem all right. So we can accept what has come out. And this is standard regression output that most software packages will spit out for you. The things we're going to look at are the estimates. BMI does seem a useful predictor. And what we can do using our model equation is to actually write down our fitted model. So our response is glucose, mean glucose at baseline. From the estimates, the intercept is 83.3 and the slope is 0.48. So that describes quantitatively the relationship between BMI and glucose, and is the equation of that straight line through the data points. And there's the line there in the plot on the right-hand side. So what can we do with that equation? Well, we can predict mean glucose level at any BMI value in the range of our data. So for example, if we take a BMI of 40 and ask what the glucose level is predicted at that level, we put 40 into BMI, and together with our model parameters, we get the answer of 103, which you can see marked on the graph there. So that's simple linear regression, and that's the model equation from a model like that. So let's just, before we go any further, talk about this word linear. Linear certainly means a straight line. No one is going to disagree with you on that. But when we're talking about linear models, as we are today, there's a bit of a technical overlay on that. And a linear model is one where you can express the right-hand side of the equation in the form of this sort of pattern. So parameter 1 by predictor 1, parameter 2 by predictor 2, and so on if there's more predictors. So that's what a linear model has the form of. And so you can see that from the simple linear regression model we just fitted, that's in that form because we've got the parameter beta1 multiplied by predictor. So there's only one predictor, but it's in the form of a linear model described above. If we were to put a second predictor in, and let's say we put in BMI squared, we've still got parameter 1 by predictor 1 plus parameter 2 by predictor 2. So it's still in the form of a linear model. So that second equation is actually a linear model. It's linear in terms of the parameters, but if you graphed it, this BMI squared would result in a quadratic. It'd be a curved line on the graph. But linear in this context refers to the parameters. Now, if you look at this model at the bottom here, which is used or can be useful if you're looking at weight over time as weight's being lost, the beta naught as the intercept is sitting at the front. Beta 1 is there, but the beta 2 is caught up in the exponent at the top, and so that can't be put in the form of the pattern above, and so that is not a linear model. So all the models that we're going to talk about today have this sort of general pattern where you can write the model equation as an intercept plus parameter 1 by predictor 1 plus parameter 2 by predictor 2, etc. So let's ask another question. Is age a useful predictor of glucose level as well as BMI? Well, let's have a look at a graph because that's always the first thing to do. In the bottom row here, we've got glucose against BMI, which we just dealt with, and now we're going to add in age. Well, it'll be interesting to see what we get from there, but we can put in a straight line. It may or may not be useful, or at least there seems to be a very weak relationship between glucose and age, but it doesn't, that pattern does not suggest that we should not put a linear model through there. So when we do that, we add age in as well. Our model equation is intercept plus beta 1 times the first predictor BMI plus beta 2 times the second predictor age. And when we fit that model, we get the estimates for the three parameters, and the fitted model equation is what's on the bottom here. So again, this is just an extension of a simple one predictor linear model. Now we've just moved into two predictors, but the model takes the same form, and both of these predictors are continuous. So when we look at what we can do, you can take the fitted model equation using those estimates we got, and you can say, well, for someone who's 60 years old with a BMI of 40, what's the predicted mean glucose level? And you put in the age and the BMI, and together with the parameter estimates, we get the predicted mean value of 102. And because we've got three variables here, you can actually look at this in 3 dimensions, and you can see that there's not much of a slope in the age direction. When we look at that plane there, the plane is the fitted model and the blue points the data. And if we were looking at an age of 60 and a BMI of 40, then you can see that we're about 102 on the plane there. So that's how we can use that model with two predictors. It's just an extension of the model with one. Now let's ask a different question with a slightly different twist to it. Does exercise affect glucose level while adjusting for BMI? In this case, we've got a continuous outcome, same as before. And we have BMI, which is a continuous predictor variable. And this time we have exercise, but exercise is a categorical variable. It has two groups in it. And so people would normally call this an ANCOVA, an analysis of covariance model, because we're looking at the effect of exercise on glucose while adjusting for BMI. So let's fit a model to that and look at whether exercise affects glucose in the presence of BMI while adjusting for BMI. There's the data with the two exercise groups coloured differently, and it's a bit hard to tell what the difference might be there, but we'll just fit the model for purposes of illustration. But the question is, well, what model are we going to fit? There's various possibilities, and it depends on what the relationship between the variables is, the predictor variables is. On the left-hand side here, this scenario would apply if exercise had no effect at all. So if there was no difference between the two groups, then the relationship would be determined solely by BMI. If we look at the middle plot, this is a situation where the glucose level for the two groups increases at the same rate. And that's shown by the two parallel lines. So that for both the no exercise and the exercise groups, as BMI goes up, glucose level goes up at the same rate. But the two groups are separated by constant difference. So that's the difference between them. There's just an upward, or there's a constant difference between the two groups. So there's like just an adjustment for the two groups. The third possibility is that the glucose level increases at different rates for the two groups. And so there you've got two lines that are not parallel. So what would the characteristics of these lines be? In this middle case, you'd have parallel lines, which means they have the same slope but different intercepts. In the case on the right, you've got two completely different lines, so you'd have different slopes and different intercepts. We're just going to fit the scenario in the middle. So we're going to fit a model that will fit parallel lines. So what have we got? Two predictor variables, BMI, which is continuous, exercise, which is categorical, and our model equation. Well, we can write it in exactly the same form as we wrote the equation before, where we had two predictors. We have our intercept, we have the coefficient for BMI, and we have a term for exercise. And when you think about that plot on the previous slide, what this term is doing is telling us about the gap between the two lines. Exercise is coded as 0 or 1. So the no's get a 0 and the yeses get a 1. And if you remember from last month's seminar where Eve Slavich was talking about interactions, she talked about these variables that are coded as zeros and ones. They're dummy variables or indicator variables. And they're used when you've got categorical variables. And exercise here is one of them. So that's how we can write our model. And it's a linear model. It looks exactly like the previous model where we had two continuous predictor variables. So what happens then in relation to these two groups? Well, for the no exercise group, for the no exercise group, this exercise value is 0 because that's how it's coded. And the equation reduces to this, beta naught plus beta 1 BMI. For the exercise group, the exercise variable is coded as 1. So we get beta naught plus beta 1 BMI plus beta 2. And if you rewrite it like that, and you compare these two equations, you see that what we've got is two lines with the same slope, beta 1, and different intercepts. So that's the model we're fitting. But it's all come from this model equation here, which is just a linear model equation with two predictor variables. And when we fit that model, we get our estimates, and plugging the estimates into the model equation, we get our two straight lines. And you can see they both have a slope of 0.47. The no exercise group has a slightly higher intercept than the exercise group, as we might think would be the case. And that's what it looks like on the data. So now, supposing we ask yet another question and say, well, does exercise alone affect glucose level? And you'd think, well, okay, what does this mean? We've got glucose as a continuous outcome. We've got exercise as a categorical predictor, but it's only got two groups in it. So we can do a t-test. That'll answer the question. We make a plot of the data just to see what's going on. T-test looks like it would be right, but instead of doing a t-test straight away, we'll do a linear model instead, because we can. The response is glucose, and the predictor is a categorical explanatory variable, which happens to have two categories. And so here's our model equation. We have an intercept, we have an indicator variable for exercise, and its parameter attached to it. So it's exactly like the equation before where we had BMI in it as well, except now we don't have the BMI. And when we run our linear model, this is the outcome that we get. We get the estimate for the intercept, and we get the estimate for the coefficient for exercise, yes. And then we can get our estimated means, because what this model will give us, since we've only got categorical predictors, is we get estimated means for each of the categories for our response. So using the estimates for the exercise no group, the exercise variable takes a 0 value, so that the mean for the exercise no group is given by the coefficient alone, sorry, the intercept alone. And for the exercise yes group, the variable takes the value 1. And so we have to add the two parameter estimates together to get the mean for the exercise yes group, and we get 95.7. Now, suppose we want to go into the software and pull up the t-test routine and just run the whole thing as a t-test, because it's there ready-made as an option for us. Here's the output. So what do we get? The mean for the no group, 97.4. Mean for the yes group, 95.7. It's exactly what we got before. So we're getting the same estimates out. But the more interesting thing is the test statistic in the t-test is 3.775. And when we look at the linear model, it's the same thing, except the two routines have just done the subtraction of the two groups differently. They've just ordered the two groups in different ways. So the linear model is basically giving us exactly the same routine as the t-test, exactly the same output and results as the t-test. And so you can see that a t-test is just a linear model. It's a special case of a linear model. It has one categorical predictor variable with two groups. But when you look at the model equation, it takes exactly the same form as a simple linear regression equation, for example, but instead of a continuous predictor, we've got a categorical predictor. Now, what's missing from all of this? Well, we can't stop without mentioning ANOVA, which is an extension of the t-test. What happens if you have more than two groups? Well, you can't do pairwise t-tests. That's very inefficient. You would move on to using ANOVA. And the question here is, well, does a subject's physical activity level compared to other women of similar age help to explain their glucose level? This is based on a self-rating by the subjects at the beginning of the study. And you can see a sort of a fairly clear trend that as physical activity goes up, glucose goes down. So we'll fit a linear model to this. This would classically be called an ANOVA because we have a continuous outcome glucose with a categorical predictor value with more than two categories, but we'll just use a linear model for it. And it's just an extension of what we did with the case where we had exercise as the explanatory variable. So how it works is we have 5 parameters because we have 5 categories. The intercept relates to one of the categories, just as it did in the case of exercise. So it's going to relate to the first category, much less. It'll be the mean of the first category. And then we code the other 4 categories with indicator variables. So a variable for less, equal, more, and much more. And so here's our model equation at the bottom. We've got our intercept and we've got a parameter with each attached to each of the other 4 categories. And it's just another linear model equation. Now, let's just have a brief look at what the software does. The software turns these categories into these indicator variables. And let's look at the baseline or the lowest level, which was the much less level. Like we saw on the previous slide, it's related to the intercept alone. And so these 5 columns are actually what software uses to do the number crunching. And so it gets much less. The first or the reference category gets a 1 for the intercept and 0s for all the other categories. The next category up is less, and it then has a 1 for the intercept, a 1 for less, and 0s for all the other categories. Equal, a 1 for the intercept, a 0 for less, 1 for equal, and 0s for the rest. So that's what we'd expect to see. And when we fit the model, fit our linear model, and put the estimates into the equation, here's what our model equation looks like with the estimates. And from that equation, we can get the estimated mean for each of the 5 rating groups by putting in 1s and 0s as we need to. So to get the mean for much less was the intercept related to the intercept, and all the other x variables take the value of 0 for much less. And so there's our mean. For the less group, we have the intercept. This variable x less takes 1 and all the others take 0. And so we have our fitted mean there, and so on for the other 3 categories. For each category, its indicator variable takes the value 1 and the others take the value 0. So all of these models are linear models. They're fitted in exactly the same way. They're really exactly the same type of model. And there's really no reason to think that they are different types of model that do different types of test. They all do exactly the same thing, and they can be fitted in exactly the same way. I used R software to do all of these, and I used the single function LM in R to do the lot. In SPSS, if you use the menus, you can go to General Linear Model Univariate, and I used that to do all the analyses. When you look at the code that SPSS spits out, it uses a single command to do everything that I've done today. It's the uni ANOVA command. So you can see that software does all of these things as the same model under the hood, and that it really is a bit of confusion really to talk about them as different things. It's not surprising though, because textbooks and stats courses still do separate these things out into different types, in inverted commas, of analysis. But it helps, I think, to try and see the commonalities there. And I think as far as what comes out of this in a practical way, if you think about the research questions you have and the variables in your data that you've got to answer those questions, if you think about the relationships between the variables and how you use those relationships to answer the research questions, then this whole modeling world will, I think, become simpler, because you'll focus more on the relationships between the variables rather than what the particular name of the model might be. So I hope that's been helpful, and let's hope that software and textbooks start catching up.
Thank you so much, Peter. That was a wonderful seminar. If you have any questions for Peter, please either put up your hand and you can say them live, or put them in the chat. So we've got one question from Tanya. It says, what do the t-values mean in the ANOVA regression table, page 27, she thinks?
Those t-values there are actually testing whether the parameter associated with each of these variables is 0 or not. So it's telling you that, for example, well, that's what it's telling you in this situation. It's the t-value for the hypothesis test that the coefficient of that indicator variable is 0. So that's what it really is saying to you. Is that clear enough? Is that answering the question the way you wanted it answered?
Perhaps the confusion is that you don't have an ANOVA table with your ANOVA.
No, I don't have an overall p-value for the model, and I didn't do any contrasts where I'm looking at which levels of activity might be different from which other levels of activity.
Any other questions?
Can you please talk a bit more about ANCOVA as well? Because I don't think you mentioned about that.
Oh, yeah. This scenario here, ANCOVA is where you have some outcome and you have some explanatory variable, but you have all of these other variables, or you might have one or more other variables that you want to use as control variables. Like you think there's a particular variable, a particular predictor variable is important in explaining what's happening to the outcome, but there are these other variables, for example, that might also have an effect that you need to control for. So in this scenario here, we were interested in the effect of exercise on glucose, but we thought BMI might have an effect as well. And so we were going to use BMI as a controlling or an adjusting variable. And when you do that, basically it means you put the two variables, in this case, into the analysis. So we're interested in what, we're interested in what the effect of exercise is, but we also have to put in this controlling variable, which when people talk about ANCOVA is usually a covariate or a continuous variable. And and BMI is a continuous variable. So this is what people would usually call an ANCOVA model, because it has a combination of covariates, in this case BMI, and categorical variables in there that we're interested in looking at the effect of, but after controlling for the continuous variable that we've put in there.
Okay, thank you. And you've got multivariable linear regression. My question might not be relevant to the t-test and regression, but I just wanted to confirm about the semantics. So multivariable linear regression, that's what I would call it as well. And and sometimes it's called multiple regression.
Yeah.
But I have also seen people calling it multivariate regression. So do you want to confirm my what I'm thinking about? Things.
I perfectly agree with you.
Yeah, do you often see that in the papers and the manuscripts that you review?
Well, I don't review stuff much, but I take your point. I totally agree with you. People use lots of different words, and that's exactly the reason I'm doing this talk, because a lot of words get thrown around that are different words, but they're actually talking about exactly the same thing. And that creates a lot of confusion, which is where I started when I spoke about someone who was saying, well, what are all these different techniques and when do I use them? But you're right, and you need to actually know what the techniques are, because people still use these things, and it's important to use the terms correctly. The people make a distinction between multivariable and multivariate, and the usual distinction is that when we've got a lot of predictor variables, we call it multivariable, and if we've got more than one response or outcome variable, we call it multivariate. So if you're doing a ANOVA, for example, a multivariate analysis of variance, then you would have multiple outcome variables in that analysis. And ANCOVA and multiple linear regression are like almost alternatives in a way, except, yeah, they're almost interchangeable. I suppose multivariable linear regression is a more general term. ANCOVA has the connotation of putting a variable, a particular continuous variable, into a model as an adjusting variable. That's really where I think, correct me if I'm wrong, someone, but that's where I think the idea of ANCOVA came from. But really it's just another multivariable linear regression model.
Thank you.
There is another question. Can you see your chat, Peter? It's a bit long.
Hang on. Lost the chat window.
It's hard to find when you're sharing screen.
Oh, yes. Oh, yeah, I see it. Thanks. Yes, oh, it's an interesting question. I suppose in broad terms, yes. I suppose it's not unusual for models. Well, models get updated by new data all the time. Climate models are a classic. And so as more data becomes available, you add it in to the analysis, and that, as you say, updates the model and the model outcomes, and you can see what effect that has over time.
I would think you might worry about multiple testing. So if you've milled a model and you add to it every day, you know, your possibility of having a false positive. If you look at a significance test every single day, we know that 1 out of 20 significance tests will be positive by, you know, as a false positive. So you would want to plan that really well, and how often you update the model and then adjust p-values according to what you want to do. And Peter mentioned, Peter Humberg as well, said a Bayesian model might do better in a situation like this. Yeah, they're more sort of built for that kind of situation.
Yeah, that sort of brings in the tyranny of p-values, doesn't it? And I mean, if you're interested just in the estimates, you could see how the estimates change. But yeah, p-values are a mire.
Okay, maybe we'll wrap it up there. Thank you everyone for coming. We're going to put the lecture notes and the video on our website, so you can access it another time and pass it to anyone if you like. Thank you again for coming, and yeah, we'll see you next month as well for our next seminar, which will be on designing surveys and analyzing survey data.
Thanks a lot, everyone.